everyone. So today we're starting a new unit in Chapter 4 on sequences and series. We're in the first lesson and it is an introduction into sequences. So first we're going to define a sequence. And a sequence is a function whose domain is consecutive integers usually starting with 1, and whose range is the terms of the sequence. And usually, or I should say sometimes, following a pattern. The ones that are following a pattern are certainly the ones that we're going to be interested in. So the ones that are following a pattern are the ones that we're going to talk about the most. So let's take a very popular sequence called the Fibonacci sequence. Now, so if I'm looking at term numbers, the first two terms are 1 and 1. And then each subsequent term is made by adding the previous two terms. So if I take 1 plus 1, I get 2. 1 plus 2, I get 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 is 21. And I can keep going. I'm just running out of space here. So in the blue here, this is my range. These are the terms of the sequence. The domain is going to be the in values, 1, 2, 3, 4 consecutive integers that tell me what term I'm at. This is the range. So for instance, right here, 2 is the third term of the sequence. And I would say 21 is the eighth term of the sequence. So you see that the domain are just a list of the consecutive integers that tell me where a term is in the sequence, and the range is the actual term value. So let's take a look at an example. It says, given the sequence, identify the following term values. So a sub 1, the first term, is 3. A sub 4 is 30. A sub 7, so 1, 2, 3, 4, 5, I have 6. What would that next term be? So let's see if there is any pattern going on. If I go 3, 12, 21, 30, I notice that every term I'm adding 9 every single time. So if I want to know that next term in the sequence, I'm just going to take 48 plus 9, giving me 57. Okay, now I am asked to find a sub 11. That's going to be a little bit of work, not a ton, but if 57 is my 7th term, I'm going to go down here and do some work. No, I have some space here, 57. That's my 7th. Here are my 8th, 9th, 10th, 11th. So I'm going to have to continue to add 9 for a few more steps. So if I add 9 to 57, I'll get 66. If I add 9 again, I'll get 75. Add 9 again, I'll get 84. And if I add 9 one more time, I'm going to be at 93. So a sub 11 is 93. So this notation right here, this a sub, a number, so 11 again represents the 11th term. A is usually what I'm going to call a sequence, and we're going to do some specific notation here in a minute. So here it says, since each term value is paired with exactly one term number in the sequence, we can think of a sequence as a function like we defined it in the previous slide, where the domain is the term number. Those are the consecutive integers here. And the range is the set of term values. That I see here in that second row. So n is I can highlight that for you guys just in case you didn't see it. So here n, term numbers are my domain. A sub n, the term values here, are the set of values in my range. And those are the values of the sequence. All right, so let's look at an example. It says, Karen has been doing crunches and recording the numbers she completes each day for the last week. So here, since the first term is 20, that means on the first day, she does 20, second day 22, third day 24, and so forth. So describe the pattern in your own words. So as I'm looking at these values, I can see that each term is 2 more than the previous term. This type of a description of a sequence is called recursive because it's based on a recurring pattern. Although the description is correct, we can shorten it if we use a standard notation, which we're going to be able to use for all sequences. So here's my sequence: 20, 22, 24, 26, 28, 30, 32, etc. So A initial is equal to 20. This is the first term in the sequence. A sub next, or the next term, is equal to, I'm going to say A sub previous, the previous term, plus 2. So every term, I just look to the term before it and I add 2. Therefore, we get our recursive notation for a sequence. It's going to look like this. I'm going to use a set bracket because this is a set of values. I'm going to set my A value, my first initial value, A sub 1, equals 20. And then what I'm going to do is I'm going to set my rule. So when I set my rule, I'm going to say A sub n, because A sub n stands for the nth term in the sequence. So that what I'm getting ready to write, setting my rule here, should work for any term. It is going to be equal to, I said A sub previous before. So if I'm at the nth term, the previous term would be A sub n minus 1. So that stands for the previous term. And now I need to say I have the previous term plus 2. And then I need to set my domain. So my n value is going to be greater than 1 because I started with A sub 1 right here. So my next value will be 2, and then I can go up to 3, 4, 5, etc., all the way up to infinity. So this is my formal notation. This is, I should make sure I put this somewhere, that this right here is a recursive notation. And it's a recursive notation because it is a rule in which one or more previous terms are used to generate the next term. So that's what recursive notation is. It's a rule where you're using previous terms, one or several previous terms, to generate the next term. If I were to go back to that Fibonacci sequence that I had before, let's take a look at that and see if I could come up with some sort of recursive notation. So here I have 1, 1, 2, 3, 5, 8, 13, 21, ... So here, for my notation, I'm going to have to set the first and the second values because every term is related not to just the previous term, but the two preceding terms. So I'm going to have a sub 1 is equal to 1, and a sub 2 is equal to 1. And then I can say a sub n is equal to a sub n minus 1 plus a sub n minus 2, such that n is greater than the 2. So I would be starting with 3 and adding the two previous terms. So this is one term before n, and this is two terms before n. And let's check it out and let's make sure it works. Let's say I was trying to find a sub 6 for my Fibonacci sequence. Well, based on my rule that says I'm going to take a sub 6 minus 1 plus a sub 6 minus 2. Well, 6 minus 1 is 5. 6 minus 2 is 4. Now, a sub 5 is the fifth term in the sequence, so that's going to be 5. And a sub 4 is 3. I add 5 plus 3 and I get an 8. Let's just make sure that is indeed the sixth term in the sequence. So our rule works. So this would be the recursive notation for a Fibonacci sequence. All right, so let's take a look at my next two examples. It says find the first 5 terms in each sequence. I'm actually going to make this pretty big. All right, let's take a look at number 1. It says a sub 1 is 17, and a sub n is equal to a sub n minus 1 plus a 4. So I'm just adding 4 every term. So my first term is 17. If I add 4 to 17, I get 21. If I add 4 to 21, I get 25. Next would be 29. And next, if I add 4, I'm at 33. So those are the first 5 terms of the sequence. And let's look at the next one. It says a sub 1 is 8. Now it says a sub n is equal to 3 times a sub n minus 1 minus a 1. So I'm going to take 8 times 3, which is 24, subtract 1, and that gives me a 23. Now for the next term, I'm taking 23 times 3, which is 69. Take 69 minus 1, and I get a 68. For the fourth term, I'm taking 68 times 3, and that's 204. Then I subtract 1, and I get a 203. And then for my fifth term, I take 203 times 3, that's 612, subtract the 1, and that's 611. So now I've done the first 5 terms in each of these recursive sequences. Here, in the next example, I want to describe the sequence in words and then write the recursive notation for the sequence. So in the first one, I've got 17, 20, 23, 26, 29, 32. So I can see the pattern where each term I'm adding 3 to the previous term. And I can see this works throughout. So for my notation, I'm going to say a sub 1 is equal to 17. And a sub n is equal to a sub n minus 1 plus a 3. And I'm going to set the n is greater than 1. Some people will put an n is greater than or equal to 1 here, which is completely fine. It's not wrong. It's not necessary, but some people put greater than or equal to. Now let's look at number 2. So here I have 81, 27, 9, 3, 1, 1/3. That 1 to 1/3 is helpful. So I can see that each term is being divided by 3. So you're dividing by 3 each time. Or you might look at this and say you're multiplying by 1/3. Because dividing by 3 is the same thing as multiplying by 1/3. So we'll write that both ways. So if I'm saying divided by 3, I'll have a sub 1 equals 81. And a sub n is equal to a sub n minus 1 divided by 3, where n is greater than 1. If you looked at this and you saw that it was being multiplied by 1/3, so I'm going to write a sub 1 is still 81. A sub n is equal to 1/3 times a sub n minus 1, such that n is greater than 1. So both of these recursive notations work for this sequence. All right. So a rule in which the nth term is defined as a function of n is called an explicit formula for a sequence. And an explicit rule is going to be really useful because it doesn't require that you know the previous term. You can plug in your n value, whatever step you want, and if you plug in that term number, you're going to get the term value. So here I have an example. Which rule gives the total number of squares in the nth figure of the pattern shown? So here in the first figure, I have 1 square. In the second figure, I have 3. In the third, I have 3, 4, 5, 6. And here in the fourth, I've got 10. So you can see, if I were to make a chart with my n and my a sub n, 1, I'd have a 2. Second step, I'd have a 3. Oh, I just made that really small. Hold on one second. I have a 3. There we go. In my third step, I've got 6. And in my fourth, I'd have a 10, and I'm going to put dot, 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 because I'm sure I could write another figure. So when I'm looking at 2, 3, 6, 10, I don't see an immediate pattern right off. I'm not adding the same number every time. I'm not multiplying the same number. So let's just choose, I'm going to choose the 4, 10. Now, if I have an explicit formula, that means I should plug in a 4, and whenever I simplify, I should get a 10 back. So let's check letter A, my first choice. A sub 4 equals 3 times 4 minus a 3. Well, 3 times 4 is 12, and 12 minus 3 is 9. So this does not represent my sequence, just because it would have to match all of these, and it doesn't even match the one that I've plugged in. Let's check out the next one. Does a sub 4 equal 10? I'd have 4 times 4 minus a 5, and 16 minus 5 is 11, not 10. C, a sub n equals n. Well, that would mean that if I plug in 4, I'd get a 4 back. That doesn't work. So by process of elimination, D must be my answer, but let's check. It says a sub n is equal to 4 times 4 plus 1 all over 2. So 4 plus 1 is 5 over 2. I get 20 over 2, which does indeed equal 10. So it works for the last one. Let's just make sure it works for the others. If I were to plug in 3, for instance, I would have 3 times 3 plus 1 is 4 over a 2. And that's 12 over 2, which indeed equals 6. So it's good for this term. Let's check the 2, 3. I'm running out of space here. I'm going to do it right over here. I got 2 times 2 plus 1 is 3 all over a 2. Well, there my 2's cancel. I just get a 3, and that works. And then the last one, if I were to plug in a 1, I'd have a 1 times 1 plus 1, which is 2 over 2. 2's cancel, giving me a 1, and that works as well. So it looks like this is my explicit formula. So what's nice about the explicit formula is I should be able to plug in any n value, and I would be able to see how many blocks I have in a figure. I'm going to go ahead and erase some of this so that I can visualize. And let's maybe do, let's do 20. Let me circle this. So imagine in my 20th figure, that would mean I'd have 20 squares here. I'm not going to be able to draw 20, but there's 20. And then it would look like this, ladder going up, where I'd also have 20 on this side. So how many blocks would be in that figure, or squares would be in that figure? I could just say a sub 20 equals 20 times 20 plus 1 all over 2. Well, I'd have 20 times 21 over 2. I'm going to think it's easy here to take this 20 over 10 and simplify that to 2. And then I just have 2 times 21, which is 42 total squares or blocks. So now let's take a look at these explicitly defined sequences. What I want to do is find the first 5 terms in the sequence. So for the first one, if I plug in 1, I would get a 6. When I plug in a 2, I get a 4. When I plug in a 3, I'm going to get a 2. When I plug in a 4, I'm going to get a 0. When I plug in a 5, I get a negative 2. So there are the first 5 terms in the sequence just by plugging in n equals 1, n equals 2, n equals 3, 4, and 5. So now what I'm going to do, these are the last 2 problems. I want to pause the video and I want you to find the 5 terms in each sequence, and then we'll be all done. So you can pause the video, do these 2 problems, and then come back to check your work when you're done. Welcome back. So go ahead and check your work. For the second one, a sub n equals n squared minus n plus 3, you should have the sequence 3, 5, 9, 15, 23. For the third one, you should have 1, 3, 9, 27, and 81 as the first 5 terms in each sequence. So now you should be good to do problem set 4.1 and give this some practice.